Let's take a few more shots at this butterfly. As you can see, Vera is quite accurate. And the reason is the ant was distracted as it was taking a selfie. Classic problem. Can't rely on your friends all the time. So the ant has a selfie stick up here, going to his camera phone right there, and that distance, the length of his selfie stick, is D. Okay, now the bullet is moving forward, so let's draw the ant and the bullet at 3 different times. Right. We know it's moving forward. These are just 3 snapshots of time, here, here, and here. And I'll go ahead and redraw the ant here with his selfie stick and his camera phone like that. And in the middle, I'll just draw the ant. We won't draw the whole thing. So what we're going to think about is what happens when he takes the picture. We know this sends out a flash of light, and that flash of light comes down like that. A little wave comes down, bounces off the ant, and then goes back up to the camera. So we're thinking about the time it takes delta t for the light to go down and back up. So the ant takes a selfie, and we're going to call that time delta t, and I'm going to put a p subscript on it. We'll get into y later. That's delta t p. So all we got to do is think about this in both the bullet frame and in the lab frame. So in the bullet frame, right, in the bullet frame, delta t, and again, I'll put a p on it in the bullet frame, is what? Well, it's just d equals vt. Right? In this frame, I was just sitting here, it went down d, and it went back up d. Right? So in this case, the total distance is 2d. So it's 2d divided by c, where c is the speed of light, 3 times 10 to the 8 meters per second. That was easy. Now let's look at it in the lab frame. So this is if you and I were watching this light. Right? What would we see? We would see basically the light go off and reflect off the ant's pretty shiny face and go up to the camera. Right? Well, clearly it goes further. If this were a ball, if the camera threw a ball down and the ball bounced back up, that'd be easy to explain. It would say the camera gives the ball a y component of velocity down, but in our frame of reference, it also gives it an x component of velocity. Right? But that's not how light works. In the way light works, we know, based on the Michelson-Morley experiment, we know that the ant sees light going at one speed, and we see light going at the same speed. We see the light cover more distance, but it also is going at c. And that's where weird things happen. So let's calculate the weird things. So let's now calculate delta t in the lab frame. And you can see we need this distance. We need the hypotenuse of this triangle, right? So it's going to be 2 times the hypotenuse. Hypotenuse over the speed, it's still just c. Right? 2 times the hypotenuse over c. So let's see, what is this hypotenuse? Well, let's see, if we make a right triangle here, we need that. Then we would say one side is d, so d squared, and the other side is this. But we know this whole thing is c delta t. Right? So that distance is, this is the velocity v, how fast the bullet's actually moving. Right? So it goes to distance v delta t. So that side of the triangle is, or this side is 1/2 v delta t. So we have d and 1/2 v delta t. So it's equal to 2 times the square root of d squared plus 1/2 v delta t squared over c. And there's delta t on this side as well. Okay. So it's not coming out quite as simple as it is over here, is it? Well, now we got to keep doing some algebra, keep manipulating this thing. So what I would do now is I would bring the c over here and square both sides. So I'll bring the c over and square both sides. So the left side becomes c squared delta t squared, And the right side, let's see, we're going to square the 2 to make a 4, and the square root goes away. It's going to be 4d squared, and then times, we've got to square that thing underneath. The half squares to a 4, cancels a 4, plus v squared delta t squared. All right. So we're solving for delta t squared, so I'm going to bring it over here and then divide by what? C squared minus v squared. Right? So that's why I'll get delta t squared is 4d squared over, make sure I'm not making a mistake here, over c squared minus v squared. Right? See, it's just algebra. It's just confusing algebra. And then let's see, we'll take the square root to get delta t. Delta t equals, let's see, 2d over the square root of c squared minus v squared. So we're just kind of making a mess, except notice delta t in terms of 2d almost over c. Remember, 2d over c, that was the delta t in the bullet frame, what we called the delta tp. So if I could just pull a c squared out of here, I'd have 2d over c. So let's do that. Let's get that delta t is 2d over c times 1 over the square root. And I got that c by pulling it out of here. So that's 1 minus v squared over c squared. 1 minus v squared over c squared. All right? But then 2d over c, that was delta p. So we find that the difference in time in the lab frame is equal to the difference in time in the bullet frame, but times a factor, 1 over the square root of 1 minus v squared over c squared. So we'll look at the value of this number later, but you can tell this isn't going to be 1, right? This is a velocity not equal to the speed of light. This was 24 meters per second. This is 300 million meters per second. This will be a small number, but when you subtract a small number off here, you get something a little bit less than 1, so you get something a little bit greater than 1, so they're not exactly the same. Delta t is a little bit longer than delta p. Right? So delta t in the lab frame is greater than delta tp in the bullet frame. So this is called time dilation. When you are moving with respect to an object, your time goes slower than the object. And it's not a special effect. It's not some weird computational problem. It's real. Right? So the way time flows, the rate at which time flows for different objects in different reference frames is just different. We don't notice because if you're going slow, the difference isn't very big. We'll talk about that in a minute. But it is very real. The reason we call this one P is you could ask, well, is any frame special? Right? Which is the one that's going the fastest? And there is sort of one that's special. In this case, this is called the proper frame. And the bullet and the ant are in the proper frame because the proper frame is the one where the event you're watching happens at the same place. So here we were watching the light go down and come back up and end up back where it started. In the bullet frame, it just went back to where it started. In the lab frame, it went to a different position. So certain frames have this special designation. It doesn't mean the light prefers those frames, or those are where the speed of light is c. The speed of light's always c. But we do get into cases where certain frames are preferred in terms of the way you calculate values of things. So that's what the delta p proper was all about. Okay? So next we'll look at some implications of this difference. So the effect that we just calculated is called time dilation. As a quick reminder, if you had this little setup where you have a flashlight bounce down and go back up, if you ask somebody in the frame of the moving object, what time did they see? That's delta Tp. And if you ask somebody that's in the lab frame just watching this happen, what time did they see? They see delta T. And the reason they're not the same, what we found was that delta T is the same as delta Tp except this factor, 1 minus v squared over c squared. The reason they're not the same is the one in the proper frame sees it go one distance, and the one in the lab frame sees it go a different distance, but they see it go the same speed. So the only way it can work out is that the time is different. So this term is sometimes just written gamma, right? So if we say, you could almost see it written this way, delta t is gamma times delta Tp, the proper frame, where gamma is that. And the reason we don't really notice this is because gamma, for everything we experience, is very close to 1. In fact, for this situation, where it's 24 meters per second, gamma is equal to 1.0037. That's our gamma. Okay. So it'd be very hard to notice the difference in this case. Although you can notice it if you either go faster or you can measure really small amounts of time. Because if you simply plot gamma, and you can make your own plot of this, we're just saying if you go faster and faster, v approaching the speed of light, c, from 0, and you plot gamma, put 1 here, put maybe 10 here, it can go up to infinity. But what you'd find is a plot looks kind of like this. If you say I can't go faster than c, then it pretty much stays right at 1, going up very slow until you get real close to the speed of light, and then it goes up like that. So if you're at ordinary speeds down here, it's pretty much 1. And if you go really fast, even half the speed of light is pretty close to 1. You have to get really high speeds, very close to the speed of light, to see these effects happen significantly. However, even if you're down here in this small, in this typical velocities of airplanes and spacecraft, if you can measure short enough time distances, you can detect it. And sure enough, special relativity has been checked many times. All the experiments completely agree. So it is absolutely true. But let's think a little bit about what it does to time. So you can think about a clock moving and at v. And if you watch a clock, it may bother you. You don't want to think about the hands. So just think of it this way. Pretend the clock has its own little mirror, right? And its own little light going up and coming down. And just think that's how the clock works. It sends up light, it comes back down, it takes, say, a microsecond or something, and when it detects one of those, it moves the hand a little bit. And it sends it again, and it moves the hand a little bit again. And it sends it again, and it moves the hand a little bit again. So that's what allows the hand to go around and measure time. Imagine a clock that works that way. Well, if you see this clock moving, it's exactly what we talked about here. When some interval of time occurs to the clock, delta tp, you see one that's longer, delta t, right? Delta t equals gamma delta tp. Right? So what it looks like to you is that the clock appears to go slower. Moving clocks appear to run slower. And that may sound a little counterintuitive because, let's say, it was our time that got dilated. But just think of it this way. Imagine the distance the light had to go for the clock to go around once. Right? To me, watching the clock move, I'm going to see the light go like this, a very long distance, right, as it bounces up and down as the clock goes by. I'm going to see the light do that. And I'm going to take the speed of light in that distance and get some amount of time. It takes some amount of time for the clock to go all the way around. But for the clock itself, it's only seeing the light do this. So I would say it goes a shorter amount of time. So I look at the clock and say it's going a shorter distance, but it's also at the speed c, so it's not as far. It shouldn't take as long. Right? So I see the clock moving its arms slowly, more slowly. Because to me, it's a long amount of time to take all this distance, but the clock only has to go like this. So its hands move more slowly, is one way to think about it. So a moving clock tends to run more slowly. And this leads to the famous way that you can time travel. You just get on a ship and you take off near the speed of light going away, and those of us on the Earth see you, and we see your clock running slow. You're barely moving if we're going at normal time. You turn around and you come back, and then you're only aged a couple years, and we're all long gone. Right? We're all long off, dead, thousands of years later, depending on how fast you went. This often leads directly to the twin paradox. People say, well, why did the traveler's time slow down? Why didn't your time slow down? If two clocks pass each other, which one is going slower? So this is where relativity gets really complicated, and why we're stopping here, is because it's not just time that gets altered, also simultaneity gets altered. We can't even agree on when two things happen. Do they happen at the same time? Do they happen at different times? It depends on your frame of reference. Lengths get changed. It depends on your frame of reference. Lengths get shorter. For something moving, it actually is physically shorter. And each one of these, you have to have your own little trick with the frames to explain it. This is why examples in special relativity are so contrived. You have to make up this case where it's only time dilation you're seeing, and not simultaneity and length contraction and everything. The basic answer to the twin paradox is the one that will age less is the one that has to accelerate to get back. Right? So the only way this twin is going to come back to the Earth and meet his much older brother or sister is that he had to accelerate, and then you're no longer in an inertial frame for part of the time. And then the details of how you explain that, there's lots of ways to talk about it. But basically, there's no just simple, trivial answer to all of these things. So this has just been your basic introduction to the idea of just time dilation. But now you should be set to go on if you want to read more about special relativity.